In this video, we are going to look at the example problems in the section 3.2 slides. Here, we're going to start here on page 3. So let's take a look at this problem. So here, we want to let P represent the statement 5 is greater than 3, and we'll let Q represent the statement, let's move this down a little bit, sorry about that, that 6 is less than 0, and we want to find the truth value of P and Q. Well, let's first identify the truth values of 5 is greater than 3 and 6 is greater than 0. 5 is greater than 3, so P is true. 6 is not less than 0, so Q is false. So now we go to the row in our truth table where P is true and Q is false, and we see that that means that the whole statement P and Q is false. All right, moving on from here. Now we're going to talk about some OR statements. We want to know if P is 5 is greater than 3 and Q is 6 is less than 0, what is the truth value of P or Q? So again, we know that P is true and Q is false. So now we have to figure out, is P or Q true or false? Well, we go to the row where we've got a true P and a false Q. That gives us our answer. Here, P or Q is true. Okay, next up. Now we're talking about negations. And in a negation, this one's a little more complicated. We're going to have to build a truth statement for this whole thing. But there is our truth table for not P. And we're basically just saying that that's got the opposite truth value of P. So now we want to find out if P is true, Q is false, and R is false, what is the truth value of the compound statement not P and Q or not R? So that's kind of a complicated statement. So we're going to have to build a truth table for this. We start off with our not P truth table. So if I write out P, Q, and R, then we'll fill this in not P and Q or not R. And we can fill in the truth values for P, Q, and R. True, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, false, false, false. And now, if P is true, then not P is false. And if P is false, then not P is true. Obviously, Q just follows the pattern for Q. True, true, false, false. True, true, false, false. And not R is the opposite of the pattern for R, so it goes false, true, false, true, false, true, false, true. Okay, now what I like to do next is to look at the OR between our Q and our not R. And we know that OR is true if either of the entries are true. So we've got a true false, that's true. True true is true. false, false is false. False, true is true. True, false. True, true, false, true. I'm just going to put that in a box now to distinguish it from the other stuff. And now we look at this and. We know that and is true only if both of the operators are true. Both of the things that we're connecting are true. Both statements are true. So false, true, false. False, true, false. False, 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 true, false. True, 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 false, false, true, true, true. I'll circle that. And now we know P is true, Q is false, and R is false. Well, if we look at that, that's in this row. You see the and is false. So this is a false statement. And next, we want to look at these problems on page 8. There are a couple of them. We're going to let P represent the statement 3 is greater than 2, Q is 5 is less than 3, and R is 3 is less than 8. And we want to decide whether each of these statements is true or false. I'm not going to make us make truth tables for all of this stuff. We're going to logic it out. Okay, so P is true. Q is false. And R is true. Now, not P is false and not Q is true, but that means we've got false and true, which makes this false. Not P and Q. Well, P and Q, P is true and Q is false, so P and Q is false, so not P and Q is therefore true. This next one is more complicated. We'll look at each of the statements on either side of the or. Not P and R. Okay, not P is false, but R is true. So not P and R is false. Not Q is true, and not P is false. True and false is false. False or false is false. Next, we want to decide if these statements are true or false. For some real number x, x is less than 5 and x is greater than 2. This is true because we have a whole range of numbers between 2 and 5, but not including 2 and 5 that we can look at here. 3 is one of those numbers. 3 is real. It is less than 5. It is greater than true. This is greater than 2. So this is a true statement. For every real number x, x is greater than 0 or x is less than 1. Both can be true, remember. We can have both of these statements be true about some numbers, and we do have them true about some numbers. For example, the number 1/2 is both greater than 0 and less than 1. But because both being true is fine, this is true. Finally, we're given the statement for all real numbers x squared is greater than 0, but there is a counterexample. And the counterexample is if x is 0, x squared equals 0, which is not greater than 0. Therefore, this statement is false. Now we've got some problems about constructing truth tables, so we'll do those. We start by constructing a truth table for not P and Q or not Q. So we start by writing out our P and Q, and then do that. We've got not P and Q or not Q. I want to figure out for which values this is true. So we fill in the values for P and Q, true, true, false, false, true, false, true, false. For not P has the opposite truth values from P, so that's false, false, true, true. Q obviously has the same truth values as itself, true, false, true, false. And not Q flips those, false, true, false, true. Now, we look here to see when not P and Q is true and when it's false. It's true only if both not P is true and Q is true, and false at all other times. I'll put that in a box. And now we check the OR. The OR is true if either is true. So it's false if they're both false, or false if both P and Q are true. But at all other times, one of these statements has to be true. So it's true, true, true. Put that in a circle. So suppose P and Q are true. We want to know the truth value of the compound statement. If both P and Q are true, then the compound statement is false. Our next truth table is more complicated. Not a lot more complicated. Okay, so here we have just P and Q again. And now we've got P and not P or not Q. Okay, so true, true, false, false, true, false, true, false. P just follows the pattern of P. That gives us true, true, false, false. Not P gives us the opposite, false, false, true, true. Not Q reverses the pattern for Q, false, true, false, true. Now we check this OR. Okay, here both not P and not Q are false, so this is false. False and true is true, true and false is true, true and true is true. Put a box around it. Now we compare this column, our P's, and our ORs to see where this whole statement is true. False, because we got a true false. Here it's true, and for these two, it's false. Put a circle around it. There we go. There is our truth table for this statement. Final one for this set of problems. We want to consider the statement not P and R or not Q and not P. So here we have to set up something with three variables, P, Q, R. And then we'll write in our not P and R or not Q and not P. And we fill in here, true, 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 false, 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 true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. Okay, so not P goes false, 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 true, 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 true. Same over here. Not Q goes false, false, true, true, false, false, true, true. And R goes true, false, true, false, true, false, true, false. So now we check our first AND here. False and true is false. False and false is false. False and true is false. False and false is false. True and true is true. True and false is false. True and true is true. True and false is false. And I box it. Now we check our second AND. False and false is false. False and false is false. True and false is false. True and false is false. False and true is false. False and true is false. True and true is true. True and true is true. All right. Now, finally, we check. I'm going to box this again. And then I'll check my OR. False and false is false. False or false is false. False or false. False or false. False or false. True or false. False or false. True or true. False or true. Circle that. Now, suppose P is true, Q is false, and R is true. We want to find the truth value of this statement. So we check P is true, Q is false, R is true. There we go. This is false. Next up, we've got after making a reasonable. Okay, so we want to construct the truth table for each of these compound statements. I might have. Oh, okay, I missed one. Okay, so here on page 11, suppose n is a counting number and a logical statement is composed of n component statements. How many rows will appear in the truth table for the compound statement? I'm just going to say this here rather than bringing us to the paperwork. Actually, I'll write it, but because the answer is on the next page. For n component statements, the truth table will have 2 to the n rows. And that's right here on this next page. A logical statement having n component statements will have 2 to the n rows in its truth table. Next up. Here we're asked to construct a couple of truth tables. We'll just do those on the separate pages. Construct the truth table for not P and Q or not Q. So you got P, Q, not P and Q, or not Q. And I believe we actually already did this one. Yes, we did. That was actually the first one we did. So yeah, I don't feel we need to do that one again. Let's check this next one. We've done this one as well. I'm not going to do that one again. So we can move on to the next set of slides, or the next slide. And take a look at these problems. Are these two statements equivalent? So we know that a truth that logical statements are equivalent if they have the same truth tables. So we just need to figure out the truth tables for these two statements. Okay, so I start by making P, Q, not P or not Q. Okay, so not P is false, false, true, true. Not Q is false, true, false, true. So the or is true if as long as they're not both false. So that's false, true, true, true. Next, PQ, not P and Q. True, true, false, false, true, false, true, false. So for P and Q, we can really just do this here because we know what the and looks like. If both are true, that's that's true. True, false is false. False, false. And then the or here, the not here reverses all of this. So false, true, true, true. Since each of them has the same result for the truth table, false, true, 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 these are equivalent statements. Now we've got one more set of problems to examine. We want to find a negation for each of these statements by applying De Morgan's laws. And De Morgan's laws say that not P or Q is equivalent to not P and not Q, and not P and Q is equivalent to not P or not Q. Okay, so I laughed or I cried. Not I laughed or I cried. The negation of this is going to be I did not laugh and I did not cry. Now we've got she won't try and he will succeed. Remember, we've got this and in the middle here. So the negation has to be an or. She won't try, we negate that. She will try. Or we negate he will succeed as he won't succeed. This last one is a little more complicated because first, it's given in symbolic form, and second, we've got a subnegation in the middle of it. So we're going to start by recognizing that we're going to have to take the opposite of not P, which is P, and then we make an and now we have to take this Q and not P and negate that, and for that, we get not Q or P. There is the negation. That's it for this set, for these slides. If you have any questions, please get in touch.